In this video, we're solving a vertical Atwood machine with a heavy pulley by using a force and torque analysis. So when we approach these things with an energy approach instead, that's generally a lot simpler, but energy can only compare an initial and final state. And what we want in this problem is actually the details of the motion. So using a force and torque analysis is going to allow us to actually find the acceleration of this system. And that's the point of part A in the problem. And then we're going to follow that up by finding out the total angular displacement of the pulley in the first 2 seconds of motion. So we're going to start by getting the system fully labeled up with forces. And there's actually quite a lot to do here. We're going to start with that 180 gram mass hanging off the left side. Note that's the heavier mass, so we know which way this whole thing is going to evolve. That 180 gram mass is going to fall while the 125 rises and the pulley rotates counterclockwise. So for this 180 gram mass, I want to be able to keep things symbolic in most of my calculations, so I gave it a name of M1. That means the weight is M1G. And then I called the tension in that side of the string T1. Note that with a heavy pulley here, the tension on each side of the system is not going to be the same. In fact, I already know that T1 is going to be greater than the tension on the other side of the Atwood machine because I need a net counterclockwise torque to explain the angular acceleration of this heavy pulley. So next we're going to do the 125 gram mass. And of course I called that M2 and the weight there is M2G. And we called the tension in the string on that side T2. Note that I tried to make this qualitatively correct by making T2 less than T1. And that's going to guarantee that counterclockwise torque on the heavy pulley. So of course, strings are going to pull at both ends with the same tension, provided the string is relatively light. So that left string is pulling down on the left side of the pulley with a tension of T1. That's exerting a counterclockwise torque. And the right string is pulling down on the right side of the heavy pulley, and that's producing a clockwise torque. But with T1 being bigger than T2, that's a net counterclockwise torque. So next, in order to get my sign conventions consistent as I write down equations here, I'm going to use the actual physical direction of acceleration as the positive direction for all three of these objects. So I like to go ahead and explicitly put these vectors into the diagram. The mass on the left is going to be accelerating downward, so I'm going to call that the positive direction. And that guarantees that my unknown A is going to be a positive number. I do a similar thing on the right-hand side. I know the acceleration of that mass is upward, and I'm going to call that the positive direction for the analysis. So that makes it so that A is a positive number as well. That makes it a consistent definition of A. And then we have the angular acceleration of the pulley that we call alpha. That's counterclockwise here, and we call that the positive direction for the angular acceleration. So now we're ready to apply Newton's second law and the rotational equivalent of Newton's second law to all three of these pieces. That's going to give us a system of three equations and three unknowns. A is one of those unknowns, and we should be able to solve for it. So we start with the analysis on M1. And again, I'm using downward as positive for this guy. So I have an M1G counting as positive minus T1 is equal to M1A. Then we look at the analysis on M2. We use upward as positive for that guy, guaranteeing that the A is positive in both of these equations. That's really important to have the same sign on A in every equation. And this one's going to be T2 minus M2G for the net force, and that's equal to M2A. So that's just Newton's second law applied to the two hanging masses. Now we have to look at the rotational equivalent of Newton's second law, and I'm going to go ahead and call the mass of the pulley just big M here. And the rotational equivalent of Newton's second law says that the net torque is equal to the moment of inertia times the angular acceleration, or tau equals I alpha. So I'm going to define counterclockwise as my positive direction for torque. And the torque exerted by T1, that's a force of T1 exerted through a lever arm of the radius of that pulley, which we called little r. And just a quick note here, strings are always going to come off pulleys tangential to the pulley, which automatically makes them perpendicular to the lever arm. And that's why our expression for torque is so simple to write down. It's just going to be force times lever arm there because they're automatically at 90 degrees to each other. My clockwise torque, that's the negative direction, that's going to be a T2 times R. And this is equal to the moment of inertia of that disk, and I'll just plug it in a later step. So that's I times our angular acceleration alpha. Now that angular acceleration of the pulley is related to the translational acceleration of the two masses. The acceleration of these masses, we're calling that A, is the same as the acceleration of the string, but that's the same as the acceleration of a spot on the edge of the disk. So all we have to do here is think about the time derivative of our relationship between the speed at the edge of a disk and the angular speed. That's V equals R omega. And I'll post a link to the video where that was first derived. Well, if I take the time derivative of that, I find out that my acceleration, and that's a tangential acceleration at the edge of the disk, is equal to R times alpha, where alpha is the angular acceleration of the disk. Well, that A tan, the acceleration at the edge of the disk, is the same thing as A for this problem. All right, so let's make some modifications on our third equation. I'm going to go ahead and factor the R out on the left-hand side, and I'm going to sub in the moment of inertia of a disk. That's just 1/2 mr squared. So that's a big M for the disk, little r squared. And then alpha, we just figured out, can be solved for in this little equation and written as A divided by R. Again, the acceleration at the edge of the disk is the same as the acceleration of the string, which is the same as the acceleration of the hanging masses. So we're talking about exactly the same A. Now it turns out the radius of the disk doesn't matter. We can cancel one factor of R like that, and another factor of R like that. And now we have a system of 3 equations and 3 unknowns. I'll go ahead and clean up this last one just a little bit more. And our unknowns are T1 and T2 and A. Now A is what we want to solve for here, so we're going to keep that in mind as we start manipulating this system. So the first thing I notice is that I can take my second equation, so we'll call that equation 2, and I can add that to my third equation, and the T2s are going to cancel. So if I get that done, then the left-hand side is going to look like T1 minus M2G, and the right-hand side is going to be an M2A plus 1/2 big M A. But then I can take my first equation and add it to this new equation, and the T1s are going to cancel here. So this leaves me on the left-hand side with an M1G minus M2G, and on the right-hand side, M1A plus M2A plus 1/2 big M A. So then we can factor a G out of the left-hand side and an A out of the right-hand side, and we can solve for A. And we get G times the quantity M1 minus M2, all divided by M1 plus M2 plus 1/2 big M. So there's our symbolic solution. And before we plug numbers in, I just want to investigate the units real quick. In the numerator and denominator, I have units of mass. So those are going to cancel out. And my only survivor there is G, which has units of acceleration. That's exactly what we were trying to get, so I'm confident that my units are working out here. So now we can sub in numbers. We'll go ahead and use 9.8 for G, and I need to convert my masses to SI units. So M1 is going to be 0.180 kilograms, and then I have minus 0.125 kilograms, and we're dividing this by 0.180 plus 0.125 plus 1/2 the mass of the disk, which was 0.9 kilograms. And when we run the numbers on this to 3 significant digits, we find an acceleration of 0.714 meters per second squared. So note that we could just sub this acceleration back into these first 2 equations, and we would quickly find T1 and T2. But in this problem, we weren't asked for those, so all we want is that acceleration of 0.714 meters per second squared. Now in part B, I want the total angular displacement of the pulley in the first 2 seconds of motion. Well, this means I need the angular acceleration of the pulley, and that means we're going back to this equation, A tangential is equal to R alpha, where we understand there that the tangential acceleration at the edge of the disk is exactly the same thing as A, the translational acceleration of our 2 masses. So the first order of business here is to find alpha, and that's A divided by R, or 0.714 meters per second squared, divided by R, which is 0.06 meters. Again, I had to convert to SI units there instead of saying 6 centimeters. And when I run the numbers on this, I get 11.9 radians per second squared. And I want to point out something about the units here again. In this expression A over R, I have units of meters per second squared divided by units of meters. The meters cancel, and my units here are actually just 1 over seconds squared. Sometimes you'll see in a textbook that they write this as seconds to the -2 power. Well, here's where we have to remember that radians are technically unitless. So 1 over second squared is the same as radians per second squared. I just find it more intuitive to write the radians in my units for the final answer. Okay, so given the angular acceleration of this pulley, I can quickly find its displacement by using our basic rotational kinematics equation. And I'm going to write it with the theta naught moved to the left side already. So theta minus theta naught is omega naught t plus 1/2 alpha t squared. So that left-hand side is the displacement. It's the final angle minus the initial, and that's what we're trying to solve for. Now this whole thing is released from rest, and that means the initial angular velocity is 0. So all I have to do is sub in alpha and t here, and I get 1/2 times 11.9 for alpha, 11.9 radians per second squared, times t squared. So when I take radians per second squared and multiply by seconds squared, I just get radians for my angular displacement. And I get a final answer here of 23.8 radians. Now, if radians are seeming really abstract to you, it's useful to remember that a radian is about 60 degrees, which means there's a full rotation for approximately every 6 radians. And that means what we're talking about here is roughly 4 full turns of our heavy pulley. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.